So our lab number 8, it's about column theory, like how columns they behave, and columns are under compression. And there is a phenomena which is called the buckling, which I doubt that this name or word is new for you. If you guys remember back when we talked about compression, when we test compression, we simply tested compression on a very short element. The height of the element was only 2 inches, like a very small mild steel specimen. And so because of the height, we don't see any buckling. But in general, our column in buildings and basements and all of that, it's significantly big, that the height of the column is large. And that's why the larger the height, the taller the column, it will see more buckling. And our discussion in lab number 8, it focuses on buckling. So let's go ahead and see what buckling is. I start always, as usual, trying to grab some good photos for you so you can see and understand what's going on. So on the right side here, this looks like a test in compression, and we have a metal element, like a steel element, and we apply compression. And I want you guys to look at what's happening right now. So when I apply compression, there is something is happening and looks like my member is deformed, and deformed as if it was bent. Would you agree?
Yeah. Yes.
So remember, we're compressing. So compression, it means my member should get shorter. My member should get shorter. That's in compression. However, looks like although I'm applying compression, however, my element has simply bent. On the left side, that's simply a reinforced concrete column in a building, and looks like the load has exceeded the capacity of the column. And look at how the column deforms. So it's also buckling, okay? Now, before we start, let me show you what does it mean and why buckling is dangerous, okay? So if we start here and remember, we are trying to apply compression. So, okay, so my load was going here, okay, applying compression. Well, after the buckling, there is a severe problem because my load is coming here. However, my section has shifted this way. So whenever my section is here and I'm applying compression in the middle, I get centric force, I get uniform stress on the cross section. I'm asking you, what if my section moves here? Okay, moves here. See what happens? Now there is kind of eccentricity. So right now, here is my load, here is my section, and you can see there is a distance in between the centroid of the section and where we apply the force. You know what happens? This creates a bending moment on the column, and this is what bent your column. So that's why buckling is dangerous. It causes something called eccentricity. It causes deformation. It means that the shape will be deformed. We will get eccentricity, and it's kind of a chain reaction because when we add load, the load will generate buckling. The buckling will generate bending moment. The bending moment will deform your member more, and simply this will end up the life of this member here. So simply the element will fail, and that's why buckling, it will cause a failure for your member. Now, in this test here, we have few objectives, and really the objective here is to try to understand the phenomena, like what's happening there when I apply compression. Number two, try to understand something called end conditions. Okay, so watch this name, end condition. And I know that by now probably you don't know what does it mean end condition and what is the effect of this end condition on the capacity of your column. So really what I'm going to ask you is to wait for for maybe a few slides, and you will know what does it mean in the condition. And then finally there is something called Euler formula. Anyone knows who is Euler? Anyone? knows who is Euler, just like anyone knows who is Einstein or who is Newton?
Yeah, he was just like, he's a Swiss thinker that did like math and physics and astronomy.
This guy, it was an amazing guy. He was not as famous as, you know, the people like, for example, Einstein or Newton, who found about gravity and, you know, acceleration, stuff like that. But this guy has a work in everything you can think of. He was a mathematician. He was a thinker. He was he worked with physics. Amazing guy. He has one formula called the Euler formula, and this Euler formula, it is just an amazing simple formula that it's used everywhere. So anyway, I'm not gonna tell you anything more about him. He's just a great mathematician, amazing. Anyway, so Euler, he tried to study the phenomena of buckling, and you can see the phenomena of buckling is connected to structure engineering, and he came up with a formula. He called it Euler formula, and this formula, you can use it to predict the buckling or the critical load of a column. Okay, we'll look at the equation later on, but really one of the objectives in our class is to make a little comparison between the loads predicted from Euler formula against the loads that we can obtain in the lab. Okay, so Euler is telling us, you know what, this column will fail at this load. And in the lab, we can apply the load and we can see when exactly which load that will cause buckling for one specific column. And then we make a comparison. You know what, if you're not 100% sure of what I am saying, so please be patient. You will get more information shortly. So this is our test setup. So here we have a column, and my column is here. And I'm asking you, is that steel column or concrete column or wood column? Say something, please. Is that concrete column, steel column, or wood column?
It's wood.
Yeah, it's wood column. Okay, so yeah, we're taking a small bit, like maybe 4 feet or 5 feet high wood stud. You think of it as like wood stud, huh? And then we put it in this machine. The machine is kind of very old, the machine, but what it does, it simply applies compression like so on your column and see what happens. The reason why we choose wood is so elastic, so we can simply demonstrate this phenomena, and we can use it over and over and over again and again and so on. Okay, so once our column buckles, we just remove the load and then we use it over and over again. That's why we use wood. If we use steel, once the column buckles, it will be permanent, and we simply have to throw it away and use more columns, which is expensive. So that's why we use wood columns or wood studs. One more thing I want you guys to notice before we go to the next slide is the this bracket here. Okay, you can see we're looking at the bottom, what's happening here, how we connect our column to the machine, and also on the top. Okay, I want you to get the feeling, huh? Look at how the bracket is designed. So we have here a jig or bracket, and this jig is designed. You can see there is a plate, 2 plates, and those plates are kind of holding the end of your column. And we have here stiffeners. Okay, if you know what the stiffener means. Okay, so we have a stiffener. So this is the start of the discussion of the end condition. You can see we're designing the connection between the column and the machine in a way which is very strong, and you will see later on that this connection here, it simply affects the results greatly. Okay, because simply here this bracket will ensure that your column doesn't rotate in the beginning. Okay, and also on the bottom your column doesn't rotate. Again, if you're not following, there are so many chances to understand the meaning of end condition. Now let's move on. Here is our first video. So we have 2 videos in this lab, 2 videos. I'm going to show you the video. From the video, you will see the buckling phenomena. You have to understand what's going on there. And I'm going to ask you a question at the very end to tell me the difference between the test number 1 and test number 2. Please watch.
And that's pretty old right there. You can see how it's deflecting.
So can you remove the load and add it again, please?
Start again.
Yes, please.
Okay, so our first video is over. Before I show you the next video, please take a note of what is happening here at where the column is connected to the machine. Okay, this bracket ensured that at the beginning, there is a kind of a straight line, so there is no rotation. And then you can see later on, I'm hoping that you guys are able to see the curve. So the curve will start not really from the beginning, it will start somewhere here and it will end somewhere here because we have this end condition where it's fixing. So this bracket here or this jig here is fixing. It doesn't allow, it restrains, it prevents rotation at the beginning. Now I'm going to show you the second video, and which is the same thing, but we have a little difference. And please watch the video and please tell me the difference between this video and the previous one.
There's only one speed on this one. Yes.
Yeah, it's a dinosaur.
That's the tail now. So buckle, 1.67 kilonewtons.
Okay, so anybody is able to see the difference between this video and the previous video? So we still have the same wood column, same machine. Can anybody see the difference between this test and the previous video? Okay, so anyway, looks like you guys are not following, but the thing is, at the very end of the column, look at this test. Do you see the bracket? Do you see the bracket at the end of the column?
Yep.
No, I mean, I'm going to go back. Don't say yeah, because watch this. I'm going to go back to here and then run the video and just quickly take it to the end. Do you see this bracket here that has stiffeners and it holds and fixing your end of the column? Take a note of this bracket at each end, and then let's go to the next video to see. Do you see the bracket? The bracket has been removed, okay? So now If you take it to the end, you see what happens? When you take it the video to the end, you can see my column buckles on the full length. You can see, look at the curve. The curve starts exactly here and ends at the end of the column at the very bottom. While the previous video, what happened is, if you take it to the end, okay, look at the deformed shape. You can see because of this bracket, let me turn my pointer. I'm not sure if I can write something on the video. Okay, so this is the bracket. And see the column goes straight, and then here decided to make a curve, kind of a sine wave, and then come back here. While in the other video, if we started the video and go to the end, what happens here is that the column buckles, start buckling from here. You can see the curve starts from here and goes back to this point. So we have kind of full length buckling. Is that something you guys are able to observe?
Yeah. We can see
Yeah.
it.
Yeah.
Okay, so really those videos, we're trying to show you what does mean buckling, and hopefully you can see very clear that my member was pushed in this way. So it went out of my straight column before we apply load. So that's one thing. The other thing is we want to show you the end condition. How does it affect the process? It simply changes the wave deformed shape of your column. Now, let's go to Euler formula. We talked about Euler, and this is Euler formula. So Euler did some derivation and simply say, okay, you know what? Here is your critical load. If your load increased until it hits this number from this equation, then your column will start to buckle. Without any details, the equation is very simple. He said equal the B sub CR, which is your critical load for buckling, which means the load will cause buckling to happen, is simply pi squared. And you guys know what pi is, huh? Pi is simply 3.14 blah, 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 squared. Multiply by E. Anybody remembers what E stands for? Or what do we use E for?
The modulus of elasticity.
Thank you, sir. And this number here, unlike the previous test or lab, we're using here maple, and that's a different species of wood. So it's maple. And the E, we're asking you to use 11,000 MPa for E. So E here is not unknown. It is known equal to 11,000. And then multiply by I. What is I? Probably by now, all of you guys remember what is I. I is the moment of inertia of the column. And then here, down here, we have something called LE. And I know some of you may think of LE as the length of my column or the height of my column. But it is not. It is connected to the height of your column, but the end condition plays a role, okay? Anyway, at this point of time, LE is not really the length of the column. Like, for example, if I go back to my video, it is not from here to there. So LE is simply the length of the curve. If you guys remember, when we have a fixation at the end, I got a smaller curve. When I remove the fixing at the each end, so the column as this per picture, okay, so it curves from the start to the end. In this case, the curve is equal to the full length of your column. Anyway, I'll get into this business later on. For now, what I wanted to say is the critical load by Euler is equal to pi squared multiplied by the modulus of elasticity by the moment of inertia divided by the square of the effective length of your column. Now, in a nutshell, what Euler was trying to say is that the B critical load is function of the material represented by the value of the E, because E changes based on the material. Also, it is function of the shape and the size of your section for the column represented by I. Because remember, when the section is rectangular, the I is equal to BH cubed divided by 12, which means it is function of the shape, rectangular, and function of the size, where you can see the B and H. Okay. And then finally, it is function of the buckling length. And this buckling length, it is simply function of the length of the member plus the end conditions. So this is not simply the length of the member. rather than it's a length of the member affected by the end condition. Here is a good, fantastic picture to show you what does it mean, the end condition. So first of all, I need to ask you a few simple questions. Number one, how many columns do you see on this picture? Do you see one or you see two or more? How many?
Is there
Four.
4 of them?
How many? How many columns do you see in this picture?
4.
4, okay. Watch this, okay. So that's number 1, number 2, number 3, number 4. And where is your column? Is this little thing here, huh? This guy from here to there, this your column. Now you can see what we're doing here is we're trying to test different end condition. For example, the one on the left, which is number 1, you can see here we're allowing rotation in each end. So it's called bend and then bend, okay? And you can see my column will buckle on the full length of the column. So in this case, your LE, which is the buckling length, is equal to the L, which means there is something called K, which is a factor. If you multiply this factor by L, you get LE. In this case, you can see the L of the members, all of them the same, huh? So for all those 4 columns, the L is the same. The length is the same. However, the LE is different because LE is the length of the curve, okay? You can see the length of the curve here is simply the same length of the member, so which means K is equal to 1. So if I have bend condition, bend, then I get K equal to 1. Now in our, and we've done this in our lab, by the way, in the video number 2, we've done this. In video number 1, we simply add a bracket where the bracket, what it does, it simply stops, okay? Look at this. So when the column started, it started like straight line up and then start to curve later on. So that's why in this case, the length of the curve is smaller than the length of the member, which the ratio is 50%. So the LE is 50% of L. So the K in this case is equal to 0.5 if I fix that both ends. How about if I fix one end, like this one here, this is fixed, which you can look at the difference between this end and this end here right away. The slope is simply going right away this way. So you can see the curve will start right away from the support point, while here it goes a little bit straight, then later on it will bend. And that's why the length of the curve here is simply 70% of the length. So the K is equal to 2.7. The last one is kind of hard for you, and you know, number 4, it's kind of not easy. Number 4, it's fixed from one end here, but the other side is completely free. It means not only rotation, but can also move this way and this way. And in this case, your K is equal to 2. If you don't get this one, never mind. I'm really interested to teach you number 1, 2, and 3. 1, 2, and 3. So if we simply free the 2 ends, the effective length of your column for buckling will be the same as the length of the column. If we fix both of them, it means the effective length of the buckling will be 50% of the length of the column. If we fix one end and free one end, it will be 70%. Okay, now, what happens here is that you've seen Euler formula, and remember what Euler formula does, it simply predicts for you the failure load of a column under buckling. So in the lab, you will see there is a little bit of mathematical derivation where they simply come up with this term here called R, and R is the radius of gyration. Very complicated word, radius of gyration. So what is radius of gyration? To be honest, it has no physical meaning. However, it's just a mathematical term that is equal to the square root of I over A. So what you do is you take the moment of inertia, you divide by the cross-section area, you take the square root and will give you the little r. And if you simply take this part here, plug it into the Euler equation, you know what happens? You can do some derivation and simply you can end up with the sigma CR. Oh my God, now you've seen B sub CR. And B sub CR, it's the load that can fail your column in buckling. How about what is sigma? We use sigma so many times in our lab this year. Sigma, it is a stress. So in this case, we're expressing a different formulation of Euler formula. So it's the same. This is Euler formula, but the difference is in this case Euler formula, it gives you the stress at which the column will fail in buckling. Nothing new. Pi square, same, multiplied by E, which is the material, the modulus of elasticity. But because of this mathematical manipulation, we're able to get a different form of our formula, KL over R, where KL, guys, what is KL? Anybody knows what is KL? It's in my slide. What is KL? If you multiply K, which is simply could be 1 or 0.5 or 0.7, which is function of the end condition, if you multiply this K times the length of your member, you will get L sub E. And L sub E showed here in my Euler equation. So you can see here, we're using KL, or which is LE, divided by R, which is the radius of gyration. This whole term is a very popular term in structural engineering. Next year, when you learn about design courses, you will use it so often, called KL over R. And we give this whole combination, we give a name for whole combination. So the KL over R, it has a name called slenderness ratio. It tells you how slender your member is, okay? And you can see when the column is so tall, what happens? This number will get larger, which means your column is so slender. When the column is so slim, it means the area is so tiny, so the R will be small, and in this case, you get also a bigger number. So whenever you see KL over R, bigger number, what happens is your column is so slender, and it will be affected by buckling so much, which is obviously from the math. Look at the equation. Let me ask you, if this number here is equal to 10, we're able to find a sigma. How about if this number goes to 20? Does sigma goes up or goes down?
Down.
Goes down, because you can see the KL over R, it is in the denominator and it's to the power 2, which means this number, if this number is equal to 10, so this term is equal to 100, okay? While if this number is equal to 20, so this term here will be 400, and sigma will be cut by 4, okay? Will be cut down by 4. And so the more slender your element, it means it will fail at very, very low level of stress. And that's something, probably I said it one time before when we test the compression, when I showed you the curve between stress and strain in compression. I said, if your member is so short, it means your KL over R is very small. What happens is your member will fail because it yields. However, if you decide to test another specimen, which is quite taller, your KL over R will be large, and then the sigma will not be even the yield, will be very small number for the sigma or for the stress. Now, before we go to our last slide, now for the value of R, I said here R equal to square root of I over A. I have a question for you, okay? The I is the moment of inertia. You think for a given section, the I, you will have one number, or you will have more than one number? Like this I here, moment of inertia. Do we have only one number for one section, or we have more than one number?
More than one.
Okay, and it looks for some of you, maybe it look weird. Why do we have more than one number for the same section? Look at this sketch at the very bottom. So at the very bottom here, we have a rectangular shape in red, which is measured the B times. Remember, this is not the height. This is the cross section. So, I mean, this is the cross section. I don't know where to show it to you, but cross section through here. So in this picture here, you basically see the height. We're not talking about the height right now. We're talking about the cross section. So the cross section here is B times H, and in this picture here, looks like B is larger than H. Now, when we apply compression and my column buckles, does it buckle around the strong axe or the weak axe? Did you ever hold your ruler or scale, if you had one sometime, and you try to compress it? Which axe does it compress or buckles around? It buckles around the weak axe, around the weak axe. And I bet you, even if you're able to bend your ruler around YY, please look at this one. Think about this one is your ruler. So if you hold your ruler and then compress it, you know what happens? It will simply buckle this way. It means your section probably will be somewhere here, okay? Let's say it will be somewhere here. So it will buckle this way around x-axis. I'm asking you, can you do that here around YY? Like, for example, are you able to, after you apply compression, are you able to push your section this way? Hello? Okay.
I don't.
Okay, go ahead. Sorry, go ahead. Sorry, I cut you. Go ahead.
Could you repeat that part again?
So I'm asking you, if you hold, do you guys have any a ruler? I know that right now, since they don't buy those old fashioned stuff like Phi, the ruler is a scale that allows you to draw a straight line, a straight edge. Have you had any one of those?
Yep.
Did you try to compress it? And typically, since they play with it, they try to compress it and try to bend it, It's easier to bend, way easier to bend on a weak axe. What does it mean? It means it's easier to bend it this way around x-axis, which means after you apply compression, your section will move this way, okay? And it's very difficult to simply move your section about YY. Would you agree or disagree?
Agree.
Okay, so anyway, so all I wanted to say is that for the same section, you get more than one moment of inertia. We get moment of inertia around x-axis, like I sub x, which is what you do is you take the width of your beam, which is P, you multiply by h cubed to the power 3 divided by 12. And also you can get an IY. And IY is the moment of inertia about the YY axis, which is the same equation, but you simply switch the B and H. So in this case, will be h multiplied by b cubed divided by 12. I'm asking you, which one will be larger? Ix is larger or Iy is larger?
Iy.
Iy for sure, because you can see here we take the peak to the power cube, so Iy is larger. So all I was trying to say here is that I'll go back to here and say I is the minimum of Ix and Iy. And I said here weak axe, okay? My buckling will happen on the weak axe. So you should use the larger dimension of the cross-section by the smaller dimension of cross-section to the power 3 divided by 12. So you should find this number and not this number, because this is where buckling will happen. Okay, now let's go to our last part of our lab today. So really what I want to tell you, what happens is every time we get one maple column, and we have not only one, you can count them. So this is one, and I think here this is a mistake, so you can count them yourself. I think we have total of 7. So 1, 2, 3, 4, 5, 6, and 6 and 7. So we have total of 7 column, which what we did is we simply take their measurement. So we can see here, we give you the measurement 45 and 19 by millimeter. So that's the B and H. Okay, they are almost the same, very close to each other. So 45 millimeter, and the height is a little bit different, like 19 or 20 or 21. And we change the end condition. So the first one is fixed. Second one is fixed. And then everything else is bin. It means it's free to rotate. Anybody remember what will be the value of the K if it's bin condition? Anybody remembers what should be the K if you have a bin condition?
I think it's 1.
Exactly, sir. I'm going to remind everyone. Here is the picture. If you allow rotation at each end, your K will be equal to 1 because the buckling will happen on the full length of your member. So you can fill in the table, you can say 1, 1, 1, 1, 1. How about if I have fixed? What is the value of the K?
.5.
Thank you, sir. Yes, true. That's 0.5. Now, next is we also measure the length. So we go for every test and we look at, for example, this video, we measure the distance from here to there. So that is simply the length of the member. Length of the member. So we have 7 members, we have 7 length. They vary from about 4 feet. Some of them, they are 3 feet. Some of them, for example, this one is 2 feet 6 inches until I think this one is 16 inch. So they are from very tall, about 4 feet, and this one close to 5 feet. So they vary in length. And then what I do is I simply use the machine in SAT and I apply the load, and I can see once the column start to buckle, then I can record my load. So I'm asking you, this load here is what? This load here is the critical load, not from Euler formula. It is, I measure this number in the lab. Once the column start to buckle, I can measure my load. Before I show you the calculation, which is super simple calculation, I want you guys to observe what happened to my critical load as I shorten my column. Any help? Do you see what happens? As I shorten, remember, we're going from 1412 to 980 to 750, 602 to 450. What happens to my load?
Gets bigger.
It is bigger. Is that something you anticipate or expect based on Euler formula? We said it already. We said already when the column is too tall, it is too cylinder, and when the cylinderness ratio increases, what happens to the stress and the force? Simply they reduce. So the shorter the column, it will be less prone to buckling, and that's exactly what you see in the numbers here. Now let me take you through the calculation, which is really simple. Anybody doesn't know how to find the cross-section area? If you know, please help me. How can I fill this column here?
It's the base times height.
Exactly, it's simply 45 times 19, and this will give you the cross-section area. I need to remind you, please, for this lab, use Excel, because Excel is very nice. Because as soon as you program all those cells, okay, and you want to fill the entire table, anybody remembers how to do that? Let's say I'm able to program this cell and this cell, all of them, only for the first row. How can I simply fill all the table, assuming that we apply the same equation for all the sample data? It's very simple, huh? You have to mark these cells, and then simply you'll get a grip here, and simply you stretch your grip down. It will simply populate all those cells. Anyone agrees? Anybody remembers now?
Yep.
Okay, now let's move on and show you next. I'm asking you, how can we find sigma critical? And remember, all of them, they are measured. Those, they have no business with Euler. Those are our measurements. So we measure the load, and we have the cross-section area. Can I find the stress? Remember, the equation is over here. So the stress is equal to the P, so this number here divided by whatever the cross-section area. However, the tricky part is, and please write it down. Write it down, very important, the units. If we want to find the stress in MPa, I'm asking you, how can I use my P, which is in kilonewton? Any help? So remember, my area is a millimeter square, and my P is in kilonewton. How can I find the stress in MPa?
Times by 1,000.
Excuse me?
Times your P by 1,000.
Thank you, sir. That's fantastic. That's correct. All you have to do is take your load, multiply by 1,000. So in Excel, you take this number, multiply by 1,000, divide by this number, and simply you will get your stress. Okay, so you know what, I'm gonna make something will help you out. So I'm gonna call the columns. So that's column 1, 2, 3, 4, 5, okay, 6, 7, 8, 9, 10, 11, 12. And now we can have a reference for the column. So column number 7 is nothing more than column number 5 multiplied by 1,000 divided by column number 6. So you're able to fill this number. Now, anyone in the class doesn't know how to find the moment of inertia, which is column number 8? Equation is here. All you have to do is you multiply the P times H cubed to the divided by 12. So in Excel, you say this is equal to column number 2, which is 45, times column number 3 to the power 3 cube divided by 12. You're able to fill column number 8. Now, any help on how to fill column number 9, which we're trying to find the radius of gyration in millimeter? Equation is here. So the R is equal to the square root of I divided by A. We already estimated the I in column 8 and the A in column 6. So column 8 minus divided by column 6, and you get the square root. Remember, in Excel, you say SQRT. And this is a function in Excel that simply finds for you the square root. So this will be square root of the column number 8 divided by column number 6. And this will give you the radius of gyration. Now I'm asking you, can we find the KL over R in column number 10? Please say something. You guys are so quiet.
Yeah, we can.
Because K is available on column number 1, L is available in column number 4, R is available in column number 9. So this column here will be 1 times 4 divided by 9. Now you remember, here we start here, from here going this way, we look at Euler. So Euler gave us one equation, or two equations actually. One equation for the stress, another equation for one equation for the load, and one equation for the stress. And remember, those columns, which is 11 and 12, those are Euler prediction. Those are not measurement, okay? So all you have to do is look at Euler equation. It is pi squared, which you can find in Excel by typing pi and then bracket. So this will give you the value of pi, which is 3.14, blah, 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 and to the power 2. So pi squared multiplied by E. Anyone knows how much is E in this lab? Anybody was awake when I said, what is the material and how much is my E?
11,000.
Good memory. Thank you so much. It was here. Look at this. In the lab, look at this. It's Maple, and they is 11,000. So in your Euler prediction, you say pi square times 11,000 divided by KL over R square. Did I find already KL over R somewhere in my Excel file? Yes, I did. So column number 10, you square that, and you should be able to find the stress. Okay. Now, can I find the strain, the force? Okay, you can see it. Okay, one way to find the force is you need to use this equation here to find the force, which is pi squared constant multiplied by E, which is 11,000, multiplied by I, because in my Excel file, I already found the I. Somewhere here, the I is here, column number 8. And then divide by LE squared. Anyone remember where LE is in my table? Did I find anywhere in my table LE?
No, but you can calculate it. K times L.
Thank you so much. This is what I wanted to hear. So remember, LE is here. LE is K times L. In our table, we have column number 1, which is K, and in column number 4, it's L. So you can do that. However, I'm going to tell you a better or easier one. Because once you know the sigma, like the stress, all you have to do is you multiply times the area, and simply this will give you the load. That's a very well-known fact. The load will be stress multiplied by area. Because the stress is simply the force divided by the area, okay? So it's up to you. If you already figure out 12, column number 12, you can multiply 12 times area, which is column number 6. This will give you the load, but remember, the stress here is an MPa, so that's a Newton per millimeter square. You're coming and multiplying your the stress times area in millimeter square. So in this case, what will be the units of P? You're multiplying Newton, the MPa, Newton per millimeter square times millimeter square. So what will be the units of my load, or P? Newton per millimeter square times millimeter square. What are the units of P?
Newtons.
Newton. So please make sure that when you fill this table, make sure you divide by 1,000, so you're getting your load into kilonewton. Okay? And simply, I help you by giving you a sample data. So once you create your Excel file, make sure that you're getting these numbers. Once you're sure that you get these numbers, all you have to do is you scroll down, stretch this guy down, and simply you're able to fill all this table. Okay? Easy peasy. And that concludes our lab number 8, last lab for this year. Okay? Now the time is, I'm gonna probably stop the recording. And so now